We're going to switch our x3 with our xk and our xk with our x3. Really doesn't change anything on the multiplication. Thank you, Ghost, Blackboard, for going upwards. A huge thanks to Brilliant for sponsoring this video. Good morning, fellow mathematicians, welcome back to another video. So recently I created a video where I was using the so-called AMGM inequality, which is the arithmetic mean geometric mean inequality. And it sparked a lot of interest for a lot of people who actually haven't heard about it before down there in the comments section. And I thought, well, it's my purpose in life now to tell you a bit more about the AMGM and also harmonic mean HM inequality today. And we are going to prove it today, and I hope you are going to enjoy this video. And this proof I'm going to show you today is one that I came up with a few other students, with a few fellow mathematicians at my university in our third semester. It was in analysis 1, and it's a pretty good proof in my opinion. And now we are going to dive right in. So let us talk about the AMGM HM inequality and what it states at first. So we are going to say that we are in some kind of ordered field. Ordered field, like the real numbers, are basically numbers which have nice property, like they are abelian, they commute in multiplication and also addition, and this is going to be important later, that 3 times 5 is the same as 5 times 3. And more importantly, we have some kind of order induced into the field. Order means we can have some element be greater or equal or less or equal to some other element in the field. And now, for all of our sequence members, we are going to call those samples right here, because most of the time you are going to find these inequalities in stochastics, for example. We got a lot of samples, n samples, being strictly greater than 0. And then we have our AM, arithmetic mean, being greater or equal to our GM, our geometric mean being greater or equal to basically the reciprocal, you could say kind of the reciprocal of the arithmetic mean, namely the harmonic mean. And here, just take a look at these. Here we are adding all of our n samples together, and we're going to divide it by the total number of samples. This is greater or equal to the harmonic mean, which is going to be the number of samples, root, so the nth root of all of our samples multiplied together. And this right here, our harmonic mean, is just the number of samples divided by the addition of the reciprocals of all of our samples. Yeah, and this is what it states, pretty important in analysis and stochastics, probability theory, and we are going to prove it today. And we are going to go through 3 steps basically. At first we are going to prove a lemma, I would say. I wouldn't call it a lemma because once we have proven this lemma, the actual theorem becomes the lemma. So our lemma that we are going to prove at first is more of a theorem than our theorem in itself, I would say, because the AMGM HM inequalities are just going to fall from the sky. Okay, after we are done proving our lemma, you could say. But after we are done with that, we are going to make use of the transitive property of an order relation to prove our AMGM HM inequalities. Namely, I want you guys to notice something. If we prove that AM is greater or equal to GM, and then we prove that GM is greater or equal to HM, then this also implies by the transitive property of our order relation that AM is automatically greater than our HM. I mean, it does make sense. 5 is greater than 4 is greater than 3, meaning overall that 5 is greater than 3. It does make sense, right? And now we are going to dive right in, and I hope you're going to enjoy this video. And now at first, let me formulate the little lemma I prepared for you. Namely, for bunch of samples, n samples, being greater than 0, all of our samples that we use, being greater than 0, you could start this thing off with for all n element of n, and for all of our samples being greater than 0, it holds that if we have all of our samples being multiplied together, and this is going to be equal to 1, then this is going to imply that all of our samples added together are greater or equal to the number of samples. This right here is the theorem. Might seem trivial, takes a little while to prove, but it's going to be worth it a lot. And if you hear something like, for all n, there does hold something, this must tingle your mathematical senses. This just screams for our good old boy, the principle of mathematical induction. And for this, we are going to say that this right here is a proposition P of n. Okay, this is a proposition with respect to the natural numbers n. And now we are going to start off with the base case. I mean, the base case, our i's start at 1. Okay, this is what we declared it at. And now, what about P of 1, proposition of 1. Well, this just means that we have one sample, and we are going to assume that our one sample is equal to 1. Well, this obviously implies, I mean, you probably see this already, that if we add all of our samples together, this is a very lonely sample if you ask me, then this right here is greater or equal to the number of samples 1. And I mean, this right here is fucking trivial. x1 being equal to 1 implies that x1 is greater or equal to 1. I mean, this is obviously true. There's not much to argue about that. Okay, now we are done with the base case, and now we are going to assume, for the sake of mathematical induction, that for some k out of the natural numbers, our proposition up here holds. P of k holds. Now we are going to assume that for some k, element of natural numbers, our P of k holds. And now we are going to take our inductive step, and we are going to take a look at what happens when we tap our domino a step further to P of k plus 1. Then, for P of k plus 1, it does hold that, what holds? I mean, for the sake of induction, we are going to assume at first that we are going to multiply all of our samples together. Now we have k plus 1 samples, meaning we have the multiplicative chain of k plus 1 samples multiplied together. And this right here is going to be equal to 1. Now we need to take a look at two cases here, because when can a multiplication be equal to 1? I mean, for the first case, trivially, if all of our samples were identically equal to 1. So our first case that we are going to consider is case 1. All of our xi's are identically equal to 1. Well, this also means that if we multiply k plus 1 once together, this is obviously going to be equal to 1. I mean, hence our first part is going to hold still, okay, by assumption it does hold. And this right here is going to imply in the process that if we add all of our samples together, okay, we are going to add k plus 1 once together, k plus 1 times, well, 1 plus 1 plus 1 k plus 1 times, this is just going to be k plus 1. And this right here is obviously, trivially, greater or equal to k plus 1. Meaning, if all of our samples are identically equal to 1, then our induction hypothesis actually holds, which is good. But this is not always the case. I mean, not always in the multiplication must all elements be equal to 1 in order for the multiplicative chain to be equal to 1 overall. Because just as a simple example, two samples, and we're going to have two samples, one being 3, and how do we get to 1 if we multiply the 3 by something? Well, with 1/3, with the multiplicative inverse. Meaning, on the other hand, we can have that, okay, we are going to assume that without loss of generality, at least one sample in here, let's call it xi, is greater than 1, meaning we must have, thus, some xj must be less than 1 for our multiplication chain to hold. Okay, let it sink in. If we have k samples or k plus 1 samples multiplied together, and one of these is not equal to 1, but by our original assumption the multiplicative chain must be equal to 1, then another sample in this chain must be less than 1. In order for it, or just a multiplicative inverse to xi, in order for it to cancel out to the multiplicative identity. I hope it does make sense. Now, here comes the abelian or commutative property in of our samples, because at first we just assumed that some samples in here are less than 1 and another one is greater than 1. But we can get this a bit more concrete actually. If you think about it, multiplication commutes, meaning 5 times 3 is the same as 3 times 5. We can do the same thing with our elements in the field right here once again. It's a field, by definition it's abelian. Meaning, let's say for example, our x3 is equal to 3, but then our xk plus 1 that we added is equal to 5, for example. Well, we want to have those two together just for the sake of making our proof a bit easier to follow. Hence, we can just assume we are going to switch our x3 with our xk and our xk with our x3. Really doesn't change anything on the multiplication, thank you Ghost, Blackboard for going upwards, but it makes our calculations a bit easier. So we are just going to interchange elements such that they pair up as being multiplicative inverses from another. And well, this is going to help us in proving everything. And then we are going to re-index everything after changing x3 with xk. We are going to say that our x3 is our new xk. xk, and the xk is our new x3. And well, now we are going to assume once again, or more I don't know, more concrete or better. Let's say better. I don't know how to formulate it nicely. Better, we are going to assume, and all of this without loss of generality, okay? Hence my shirt comes in. With loss of generality, we are going to assume with loss of generality, without loss of generality, that xk is, for example, less than 1 and xk plus 1 is greater than 1. I mean, without loss of generality, we can assume this, and we are just going to assume that all the other elements in here are also going to turn into 1 multiplied together. I mean, this is just by the original assumption. If we just have one element which is less than 1, then we need another element which is going to be greater than 1 to cancel each other out into 1, but then we can just ignore all the other stuff, because by assumption all of the other elements multiplied together in our inductive chain are already going to be multiplied together to be a 1. Now that we got this, we are going to notice something, and this is one of the analysis things that you are going to notice that you would never notice in a normal case unless your lecturer tells you about it. We are going to notice this one and easy fact that mathematics professors hate. Namely, what about 1 minus xk multiplied together with xk plus 1 minus 1? Well, this is pretty good. This is actually pretty good, because xk is less than 1. Okay, 1 minus xk, okay, is going to be greater than 0. Then 1 minus 1/2 is going to be 1/2. It's positive. Since our xk plus 1 is by assumption strictly greater than 1, we have, for example, 1.5 minus 1 is 0.5 once again. Positive multiplied with positive is positive yet again, so this right here is greater or equal to 0. And now we can start multiplying everything out. This right here is actually equivalent to saying that we have xk plus xk plus 1, and then we are going to get, okay, a negative 1 in the process, and also a negative xk multiplied together with xk plus 1 is greater or equal to 0. And now what I'm going to do is I'm going to add those two on both sides, leaving us with one of the first inequalities right here in this last part of the proof, namely that xk plus 1 is greater or equal to xk times xk plus 1 plus 1. So why have I done this? Why did I go through all of this to arrive at what we got here? Well, actually, don't forget where we want to go overall. Where we want to go is we want to prove that p of k plus 1 is indeed true. And for this we need to take a look at the other side of the implication. Namely, we want to show that all of our samples added together is in the process greater or equal to k plus 1. Now, don't forget, by assumption p of k is already true. Meaning, if we just were to turn our n's into k's, and now I'm going to subtract our xk on both sides, you are also going to notice that x1 plus plus xk minus 1 is greater or equal to k minus xk. And this is going to help us a lot, because by our original assumption, we're going to assume that all of those multiplied together is equal to 1. We got rid of the case where one element is less than 1 by just saying that one other element is going to turn it into 1, once again, if we multiply it together. Meaning, this also implies that now that our first statement holds, that x1 plus plus, and now we got xk minus 1, and then we got plus xk plus 1 is. And now we are going to take a look at what we still got here. I mean, what we still got here is if we add all of our samples together up until k minus 1, we know that this is greater or equal to k minus xk. Meaning this part right here at the front is greater or equal to k minus xk. Turning this into an order relation, namely k minus xk plus, and now we got xk plus 1 is, this is good. We got an xk here as a common factor. And this is not bad at all, because this right here is now equal to k plus, and now we got xk times xk plus 1 minus 1 plus 1. And now we are basically done with all of this, because by assumption all of our samples are greater than 0. xk is something positive. xk plus 1, we declared this in our proof, in this case, as being strictly greater than 1. Meaning xk plus 1 minus 1 is also something greater than 0 once again, something positive. This is what we used here too. Meaning overall something positive multiplied with something positive is something positive, for example 1/2. And now we got x plus 1 plus something positive, and this is obviously greater or equal to k plus 1. I mean, it does make perfect sense, and hence we are done. We have proven our theorem because we have shown for both cases that we got here that p of k plus 1 holds true. And now, shameless plug incoming, you can use your StemMerge original QED and easy stems to put them onto your blackboard and put your little QED stamp into here. This is something that you could quite possibly do. You can find them over in StemMerge. And now it's up to us to prove the AMGM HM inequality by using our little lemma, which is actually our main theorem in this video. So here goes, let us finish it off. And at first, as mentioned before, in the structure of the video, we are going to prove the AMGM inequality. And for this, we are going to define ourselves a certain sequence, you could say. Okay, so for AMGM. And please do not forget that it still holds in the main theorem that all of our samples are strictly greater than 0. We are going to define that some sequence AI is going to consist of the following members. Namely, this is nothing other than the sample xi, some kind of sample. Okay, this is the sample being defined by other samples, divided by the nth root of all of our samples multiplied together. Okay, x1 up until xn. Might seem kind of arbitrary, but it actually does make a lot of sense if you think about multiplying all of our AIs together, namely A1 up until AN. Now what happens if we say, okay, A1 multiplied together with AN is going to be a certain product? Well, multiplying all of those together is going to leave us with, I mean, we have always a common factor of 1 over the nth root of all of our samples multiplied together. So what we are going to get down here in the denominator is, okay, we are multiplying n a's together, giving us this x1 up until xn multiplied together, this root, but to the nth power, which is pretty good if you ask me, because the nth root and the nth power really don't like each other, hence they are going to cancel out in the process, leaving us in the denominator with just a product of x1 up until xn. But this ain't bad at all if you ask me, because we are also going to multiply all of our samples x1 up until xn together by this definition. Also, so now we got something of the form a over a, which is obviously going to be equal to 1. Daddy, gotta be shitting me. That theorem is actually pretty good if you ask me, because now we got the multiplication of samples, okay, which are all strictly greater than 0. I mean, by definition of the ordered field and everything, and this definition of AIs, they are all strictly greater than 0. And this multiplication of things is equal to 1. Well, by our sneaky little theorem that we got here, this is also going to imply that if we add all of our AIs together, this is going to be greater or equal than all of our samples, so the number of samples, which is n once again. Meaning, this right here is going to imply by our little theorem that we have gotten ourselves that A1 added together up until AN is going to be strictly greater or equal, I'm terribly sorry, than n. But what is A1 added together up until AN? Well, this right here, by the definition of what we got here of our AIs, is going to result in, this is x1 divided by the nth root of x1 up until xn, and all of this added together up until xn divided by the nth root of the blah 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 once again, and this right here is greater or equal to n. Now we got a common factor once again, 1 over the nth root of all of our samples multiplied together. Meaning what we get in the process is, this right here is equivalent to saying we have x1 plus dot 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 up until xn divided by the nth root of x1 up until xn multiplied together, and this right here is greater or equal to n. And well, we got a positive number of samples. This right here this n is greater than 1. Also by definition of our xi's and the nth root right here, this right here is greater than 0, not equal to 0. Meaning we can multiply both sides by our nth root, something, and divide both sides by n, leaving us overall with our desired inequality, namely that x1 added together up until xn divided by n is indeed greater or equal than the nth root of all of our samples multiplied together. I thank you very much. AMGM inequality proven in a few lines by using the sneaky little theorem that we got here. Pretty nice, right? And the GM-HM inequality is even easier to prove, because what we are going to do is we are going to just use our AMGM inequality nicely to get ourselves what we desire. Okay, by using the AMGM inequality to our advantage, we are going to define ourselves another sequence. Okay, we are going to define some sequence once again, AI to be equal to 1 over xi. And as mentioned previously, the AM and the harmonic mean are just basically reciprocals to one another, you could say, kinda. And that's what we're going to use here. At first, let us write out what the AMGM inequality states, namely that if we have A1 added together up until AN and divided by n, we're going to get that this is greater or equal to the nth root of A1 multiplied together up until AN. Now we can plug the definition for our AI's in. Namely, our AI's tell us that this right here is 1 over x1 plus dot 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 up until 1 over xn divided by n being greater or equal to the nth root of, and now we got 1 over x1 multiplied up until 1 over xn. And now I'm going to play around with this right hand side, because this is the only hard part, you could say, about all of this. What we're going to do is we are going to acknowledge the fact that what we got right here inside the third is nothing other than 1 divided by x1 times x2 times x3 up until xn. And if we take the nth root of now this fraction, you could say, in each and every ordered field, the square root is actually nicely defined. We got that the nth root of 1, the multiplicative identity is just 1. So we got 1 over the nth root of the multiplication of the things. Meaning this right here is nothing other than 1 divided by the nth root of the multiplication of all of our samples. And well, we are basically there, because what we got right here, down here in the denominator, is the geometric mean. Meaning if we were to multiply both sides by the geometric mean and multiply both sides by the reciprocal of what we got here, we are going to arrive at what we wanted to prove. Namely that the nth root of x1 up until xn is greater or equal to n divided by 1 over x1 added together up until 1 over xn. And once again, you can use your chalk or QED stems from StemMerge to put the QED symbol under it, but this concludes the very nice proof of the AMGM-HM inequality. There are a few other inequalities like the root square mean and so on. Maybe I'm going to make a separate video on that, but those three are the most important in my opinion. And if you did like what you saw today, if you're interested in more analysis, calculus, proving different things in mathematics, then maybe our today's sponsor Brian could be the perfect fit for you. Regular viewers of my channel are probably really familiar with our recurring sponsor Brian, but if you're new to the channel, let me tell you a few things about this amazing website. Brian is an online learning platform and app which gives you access to nearly 70 interactive courses in all topics STEM, be it the mathematics that we did today, chemistry, computer sciences, sciences in general like physics, Python programming, computer sciences. Brian definitely got you covered. So it doesn't matter what you want to study, or maybe you are still in high school and want to brush up on a few topics like linear algebra, solving systems of equations, etc., then Brian is definitely the perfect fit for you. And not only do they provide you with some of the best educational and most thought out educational content out there on the internet, no, they also have a big community of avid learners who share their knowledge with other people there on Brilliant. And if you ever feel the need to go away from the courses, from the interactive learning experience and just try out something new, just try out a few exercises to get better at things like solving systems of equations, maybe making use of the AMGM inequality in some kind of application, then the community also got you covered, because they are posting new exercises daily. updating the Wikipedia pages over there on Brilliant and the like. And it's just very nice community. I really appreciate the community, and in my opinion, it's some of the best content that you got over there on the website, apart from the absolutely brilliant courses. And if this feels like it's something for you, if you feel that Brilliant could benefit your STEM career in any kind of way, then definitely make sure to check out the link at the top of the description, brilliant.org/flammable-maths, to get free access to a big portion of Brilliant already. But more importantly, the first 200 people to actually make use of the link get 20% of an annual premium subscription. And with the premium subscription, you're going to get full access to the whole website of Brilliant and all of the nearly 70 interactive courses that they got up their sleeves. And even better, they're expanding their repertoire of courses each and every month. So basically every month you are going to see a new course, or maybe an update of an older course with new animations, new interactive learning content, etc. So it's definitely worth it, and you should check it out to support the channel this way. And if you did enjoy this video, definitely also make sure to check out STEM merch for cool stuff like the Chaos Pendulum or the With Loss of Generality merch. And up until the next video, I wish you guys a flammable day. Have a great weekend and please stay safe. Ciao!